let us discuss about the initial sizing. Okay, let us discuss about initial sizing. So look here, in this initial sizing, we are doing a rubber engine sizing. What is this called? Rubber engine sizing. Rubber engine sizing is nothing but a what? We are going to it's not a fixed engine, it's a, you are going to resize the engine. Means for your any aircraft, when you're going to design, you're going to size the engine. That the process of sizing the engine is called as a rubber engine sizing. Okay, the review of sizing, refined sizing equation, empty weight fraction, and fuel weight, and summary of the refined sizing method. These are all the outline of the rubber engine sizing. Okay, so look here, in the review of sizing, what happens? So the quick method based on the configuration sketch and aspect ratio. Already you know that what is aspect ratio is B square by S. The crude estimation of maximum L by D. The approximation of specific fuel consumption, weight change during the cruise and late loiter. So this is the cruise. During the cruise, you know that already when as the mission proceeds, the fuel consumption will be there. So therefore, we have a T by W and W by S. According to that, when it is mission progresses, what happens? The weight will reduce. Therefore, we are doing a fuel weight estimation as well as empty weight estimation. That is WF by W naught, WE by W naught. Correct? And doing the loiter also. What is the loiter? It is the total time. It is nothing but a what? It's the endurance. Loiter is nothing but a endurance. And cruise is nothing but a what? Range. Okay. Weight fractions for takeoff, climb, and landing are used from the table. So weight fractions in the previously we discussed about, we see in the tables what should be the climb 0.98 for doing the climb, during the takeoff, during the landing, right? 0.98, 0.99. So we have to take according to those weight fractions when you're going to calculate by using a Brickworth range equations. That is L by C V by D ln of Wi by Wi minus 1. The first one is if you need W1 by W naught and W2 by W1. Correct? So according to that, those values will be taken from the according to the mission legs by the mission profile. Clear? See, a WE by W naught is estimated from statistical equation. What is this WE by W naught? WE by W naught is nothing but a empty weight fraction, empty weight fraction estimation. W naught is calculated by iterating process, that is called W naught is equal to W crew plus W payload 1 minus W of by W naught. This is called fuel weight estimation, and WE by W naught is called as an empty weight estimation. So the crew plus payload will not change. Why? Because the passengers who are there will be there, and also the load which is carrying in the useful payload will call that will be carried in the aircraft will not be changed. So therefore crew plus payload will not be changing. They are constant, and only the changing with the fuel as well as the empty weight with respect to the total weight of the aircraft. Okay, so here refined sizing equation. Then the refined sizing equation, what happens? See here, this is called W naught. It's nothing but a total design gross weight, we will call. It includes crew weight, fixed payload, and dropped payload. In the military aircraft such as for whenever you are going to do air to air, air to ground combat, at that time what we'll do, we'll leave them, whatever the payload, it may be the missiles, and just whatever the load what we are carrying up, that is called dropped payload we will call, and the fuel, because anyway the weight of the fuel and the weight of the empty. So therefore total design gross weight is called what? It is crew weight, fixed payload, dropped payload, and the fuel weight and the empty weight. Together it is called total design gross weight. We will call it W naught is nothing but a what? Total design gross weight. Clear? So here we can see here we are doing the fuel weight estimation as well as empty weight estimation. We are looking for empty weight estimation. So that is WE by W naught into W naught, the first equation and the second equation. Okay, and you see here there's a fixed, and this is the fixed payload, and this is a dropped payload. And next is empty weight fraction. What you are going to do in the empty weight fraction? See here, empty weight fraction versus W naught. You can see what is W naught is a total design gross weight, where the total design gross weight includes W crew, W payload, W understood fuel, and W naught, WE, that is empty weight, crew weight, payload weight, fuel weight. Clear? A is called aspect ratio, that is thrust with respect to the total design gross weight, and we know that W naught with respect to the and the surface area of the wing, that is called wing loading we will call, and M max is all with respect to the total design gross weight. Clear? So therefore WE by W naught is nothing but a what? Empty weight fraction. It's called empty weight fraction. So when you substitute these a, small b, C1, C2, C3, C4 in this equation, so therefore we're going to get what should be the empty weight fraction for jet trainer, jet fighter, military cargo, jet transport. Clear? So here Variable sweep constant we'll call whenever the if the wing having a sweep, then it's called variable sweep is called. So at that time k value will be taken as 1.04. You can see this is called variable sweep. If it is there is no sweep, then it is taken as a 1. So therefore fixed sweep as well as variable sweep, the fixed sweep as well as variable sweep. If it is a fixed sweep, then it is taken as 1. If it is variable sweep, then it is taken as a 1.04. Clear? And empty weight fraction versus W naught, and it is for mainly propeller based aircraft. We can see that this is called thrust to weight ratio, this is called power loading. HP by W naught is called power loading, is called power loading, it's called power loading. And also you can call as a W naught by WS is called as a wing loading. Understood? So thrust to weight ratio in the thrust is given in terms of horsepower in the propeller based aircrafts. Yesterday when we were discussing, we discussed clearly about it. Clear? So sail plane unpowered, sail plane powered. Clear? And home built metal, wood, home built composite, general aviation single engine, general aviation twin engine, agriculture aircraft, twin turboprop, right? There's a different type of aircraft, propeller based aircraft. So only the change when you look here, HP by W naught is called as a power loading, and this is called thrust to weight ratio. Clear? Thrust to weight ratio for jet engine aircrafts and power loading for propeller based aircrafts. Clear? Next it is fuel weight. Now we seen about a empty weight. Now we are looking for fuel weight. Clear? So engine start, taxi and take off. So whenever engine start to ground roll, and after that it will come taxiing, and it will engine starts and it will take off. During the takeoff, that is called taken as a W1 by W naught. So usually it will be in between 0.97 to 0.99. So reasonable estimation is what? W1 by W naught to 0.97 to 0.99. Clear? So subsonic Wi by Wi minus 1, that is called in the Brickworth range equation. We seen that uh, L by like V by L by D into V by C ln of Wi by Wi minus 1. This is called weight estimation. So what we are taken up, W1, 1 minus 1 is W naught, that is called, and W2 by W1, W3 by W2. It is the weight in each mission leg. So 1.0065 into 0.0325 Mach. It is M is nothing but a Mach number. And supersonic aircraft, you can see 0.991 minus 0.007 Mach minus 0.01 M square, and starting at Mach 0.1. For an acceleration beginning at the other than the Mach 0.1, the weight fraction calculated by the above equation for the given ending Mach number should be divided by the weight fraction calculated for the beginning Mach number. It depends upon that. So therefore, where the Mach number is ending and with the beginning Mach number, it is starting with a 0.01 and with the ending with a 0.991, like that. Clear? So therefore, W1 by W naught for a takeoff from the historical data, we have taken a 0.97 to 0.99. So therefore, it says that what Mach number should be divided by the weight fraction calculated for the beginning Mach number. Clear? And the next is, you can see a cruise Brickworth range equations. These are the very important equations, these two. For a jet equation, that is jet Wi by Wi minus 1 is equal to exponential of minus RC divided by V into L by D. What is this? R is nothing but a range, C is a specific fuel consumption, V is the velocity, L by D is the lift to drag ratio, where we are finding out aerodynamic efficiency of the aircraft. Clear? And this is called propeller based aircraft, Wi by Wi minus 1 exponential of R into C BHP. The B is nothing, BHP is nothing but what? Brake horsepower. It's nothing but what? Brake horsepower. Eta P is a propeller efficiency, and L by D is the lift to drag ratio. It is during cruise and loiter, it is minus lift is equal to weight. During cruise and loiter, lift is equal to weight. So therefore, L by D can be expressed as the inverse of drag divided by weight. So therefore, L by D is taken as 1 by Q CD naught W by S plus W by S 1 by Q by AE. So E is nothing but a what? Oswald efficiency here. It's nothing but a what? Oswald efficiency. Oswald efficiency. Wing loading value should be considered. So you can see this is called a wing loading, should be considered, and modified as per the situation. So wing loading value should be modified as per the situation. And in the loiter weight fraction, before we seen about that is for cruise, and now we are modifying for the loiter weight fraction. That is, we can see that it's for mainly loiter is nothing but a what? Loiter is nothing but a endurance, is nothing but a endurance. Jet Wi by Wi minus 1 exponential of minus EC, where is E is the endurance, that's total time taken by the aircraft when it stays in the air. Means the total time taken by the aircraft to stay in the air. That is called endurance. C is called specific fuel consumption, and L by D is called a lift drag ratio, and Wi by Wi minus 1, that is propeller based aircraft. We can see here again the BHP is coming up. Wherever the propeller based aircraft, we can see the brake horsepower. We are speaking about the brake horsepower, and also a propeller efficiency, where E is the endurance or a loiter time. Clear? Descent for landing for historical value. For landing, we know that 0.990 to 0.995. You can see for during the takeoff, you can see during the takeoff, it is around 0.972, 0.99. It is in between 0.97 to 0.99 for mainly for estimation for takeoff. So when you look here, so it is for landing, it is taken as 0.990 to 0.995. Any aircraft we're going to design, then these during the takeoff and the landing, this value should be taken into consideration. Clear? And landing and taxi back historical value, the Wi by Wi minus 1 during the landing and taxi back 0.9922 to 0.992 to 0.997. Yeah. And here, summary of the refined sizing method. Here we studied reviewing of sizing and refined sizing equation, empty weight fraction, fuel weight fractions. Now, just to understand how the that is summary of it. See, we are see a design objectives is a sizing mission, and this is a sketch or initial layout, the wing geometry selection and estimation. E is nothing but a Oswald efficiency, where thrust to weight ratio and the wing loading, and Wi by Wi minus 1 according to the Brickett range equation and the Brickett endurance equation. There's a loiter equations for each mission segment. The each mission segment, what are the mission segments? That is taxiing, it may be takeoff, it may be cruise, loiter, and landing, descent and land. These are all called as a mission segments. We'll call it. It's called what? Mission segments. Here S wet to the S reference and CD naught. It is called CD naught is nothing but a what? Zero left drag. It's nothing but a what? Zero left drag or a parasite drag. We'll call that is a coefficient of a drag coefficient for a zero left. It is called as a CD naught. And engine specific fuel consumption, and WE by W naught is called a weight. It's an empty weight fraction, and it's called W naught can be calculated. This is called iterative process, and it will be the understood. We are using a trial and error method, iterative for solution. So these are the complete summary of the engine sizing. Okay, so next, see, we are going for a fixed engine sizing. So rubber engine sizing, we are going to design a new engine. That process is called as a rubber engine sizing. Already engine is existed in the market, that is called fixed engine. Already all the parameters we known before itself. Either the mission range or a performance must be considered as a followed parameter. That is W naught is N thrust per engine. How much per engine the thrust is produced by a per engine, as well as T by W is nothing but a thrust to weight ratio, and range capability can be determined by the equation 2, and by considering the equation 2 is the what? This is for Brickett range equation. So what we are taken into consideration, that is L by C V by D ln of Wi by Wi minus 1. That is the equation for range. What we have considered from there, we have to take into consideration. And known takeoff weight and guess W naught, and varying the cruise legs to match the evaluated W naught. Similarly, the process may be taken for the other parameters. Yeah, this is here what happens. Total design gross weight, it is a per engine how much thrust will be produced. N is number of engines, and T by W is thrust to weight ratio. Means according to the output of the engine thrust, we are going to calculate the thrust to weight ratio. If it is a 2 engine, or maybe 3 engine, or maybe 4 engine, correct? It depends upon that. And geometry sizing, how you are going to do the geometry sizing here. When you look here at geometry sizing, the fuselage length versus W naught, and sailplane 0.86, 0.48. Here for certain types of aircraft, the fuel size is determined strictly by real world constraints, that like a passenger aircraft. Means already existence aircraft will check it. What should be the minimum length of that particular aircraft? So accordingly, we are going to take by competitive studies, we are going to take that is called fuselage length versus W naught. How much fuselage length is contributing towards the total weight of the aircraft? That is called fuselage length versus W naught. Okay, so the fuselage fitness ratio, it is what is this fitness ratio between the fuselage length and the maximum diameter versus the length of the fuselage. It is called fitness ratio. We'll call it. It's called what? Fitness ratio. Theoretically, for a fixed internal volume, subsonic drag is minimized by fitness ratio is about 3, while supersonic drag is minimized by fitness ratio is about 14. It is, what is this? There's a ratio of a fuselage length and the maximum diameter. Clear? And the wing reference area, including the area extended to the aircraft center line, is determined by takeoff cross weight divided by takeoff wing loading, W by S to the weight, that is takeoff cross weight. And next is tail area. So tail area, you can see that this is the fuselage length and this is the diameter of the fuselage, that is called fitness ratio. And we have, this is called left horizontal tail, and we have a control surfaces. We can see that CW is a wing mean chord, and BW is wingspan, and we have a SW is wing area. This is for a vertical tail, the length of the vertical tail from the center line of the fuselage. You can check here, this is a center line of the fuselage, and we are checking the what is the length of the vertical tail from the center line, and also from the horizontal tail also we are going to check. And we are going from the control surface from the center line. You can see here, this is called tail volume coefficient method, we'll call it. It's called, what's very important, it is tail volume coefficient method. So yesterday when we were discussing, tail volume coefficient is one of the most important parameter when you are going to select the airfoil in the tail, when we are selecting the airfoil for the tail, correct? We discussed regarding that. And vertical tail volume coefficient is given by CVT, is nothing but what, length of the vertical tail, surface area of the vertical tail, and span of the wing was divided by surface area of the wing. Clear? Horizontal tail is nothing but what, same length of the horizontal tail and surface area of the horizontal tail, and we have a chord of the wing as well as divided by, that is surface area of the wing. And typical values for horizontal tail and the vertical tail, and sail plane, home belt, general aviation, agricultural, twin turboprop, flying boat, jet trainer, jet fighter, military cargo and bomber, jet transport. So horizontal tail, the values, and the vertical tail values. According to that, we are going to find the tail volume coefficient by putting in the formula. We can look at what is that, LVT into SVT divided by BW by SW. So length, surface area of the vertical tail, as well as the wingspan and the area of the wing. Clear? So next, where we have to position the engine. So therefore moment arms is the left horizontal. You can see that it is called a horizontal tail, and we have the vertical tail, and you can see approximately percent of fuselage length front mounted to the propeller engine. According to that, we are going to take up the engine position, and it's around approximately 60% from mounted propeller engine. So it's 60% from the fuselage, and approximately fuselage length, it should be 60% of the fuselage length. And engines on the wing, it's around 50 to 55% from the fuselage length. Yeah, and aft mounted engines, we have a 45 to 50%. This is the engine position, where we need to position our engine. So for front mounted propellers, if the propeller is there in the front part, there will be 60% of the fuselage length we have to check. And engines on the wing, it will be 50 to 55% of the fuselage length. And aft mounted engines, around 45 to 50% of the fuselage length. Clear? And next is control surface sizing. In the control surface sizing, what are the control surfaces? We know that this is horizontal tail, vertical tail, and ailerons, rudders, and elevators. These are all the control surfaces. And also the control surfaces, we have a primary control surfaces as well as secondary control surfaces. Mainly when you look into your primary control surfaces on the wing, we have ailerons. So aileron chord versus wing chord, and we are checking sizing of the aileron. The aileron sizing, it helps in the, you know that the function of the aileron is for roll the aircraft. And we have a rudder, it is mainly for yaw the aircraft, and for elevators, pitch up and pitch down. The sizing of the control surface also plays an important role. By the historical guidelines, we can look here, we have a total span, aileron span versus wingspan divided by aileron chord versus divided by wing chord. So by that we can check around 0.6 to 0.7. According to that, it goes with a total aileron span versus wingspan, and with the aileron chord by wing chord. By that, we are going to select the sizing of that, and we are going to size the control surface area. So surface area, how much the area of the surface should be there of a vertical tail, or it may be horizontal tail, or it may be the understand the wing, it's a aileron sizing, or it may be rudder sizing, or it may be a elevator sizing. These are all comes under the control surface area. The control surface sizing we will call. It's called what? Control surface sizing. Yeah. So this is the complete the concept of the initial sizing of the aircraft. So we have to understand these are the parameters. So the first one is rubber engine sizing, and is a fixed engine sizing and geometry sizing, and we have fuselage and wing, tail area, and control surface sizing. These are all comes under in this way. And also we know that what is fitness ratio, how the engines are there, where the position of the engine, and how you need to take up. These are all with percent of the fuselage length. Clear?